What is up, everybody? Welcome to Lecture 12 of Contemporary Math. Today we're going over chapters 12.1 through 12.3. So really just diving into the introduction of statistics. To start off with, I thought we'd start with a couple of definitions. First being the definition of a population. A population, by definition, is the entire collection of things whose properties are being cataloged or analyzed. So let me move on to these these next two definitions, and I'll get into an example. A sample is really just a subset of your population. And random samples are samples chosen in such a way that every sample has an equal probability of being chosen. So, we might think of a study looking at WSU, in the student body of WSU in particular. In that case, the student body would be the population of that study. A sample might be a particular course within all the courses possible. So we might decide to look at just Algebra 1 students. That would be a sample. A random sample, however, would be a class. Because a class, there's a bunch of different classes in all different courses, right? But they each have the same probability of being chosen. So we might randomly choose samples of classes, as opposed to sample of courses, which isn't quite as random. And the entire population, again, would be the student body. Having said that, frequency distribution might then be used to say something about the data, to help us better understand the data. And as an example of frequency distribution, let's consider we're rolling dice. And we roll 4, 1, 2, 2, 3, 6, 6, 1, 2. Well, this is our data, right? These are the rolls we made. Now, we might want to talk about, like I said, the frequency distribution. And I'll explain in a second what the actual definition of a frequency distribution is. So we sit here and we're like, all right, cool. I can make a table of this. And I can write down each of these values and how often they occur. So let's do that. 1, 2, 3, 4, 5, and 6. In our data, the value 1 occurs twice. The value 2 occurs 3 times. The value 3 occurs once. The value 4 occurs once. 5 never occurs. And 6 occurs twice. So what we've got in this table is the data values as well as how much they occur. This is what a frequency distribution does. What it's really looking at is, given our data, how often do particular data values occur? How frequently do they occur? In this particular table, you might label the first column as data value, and the second column as frequency. So, we've got this data and we've written it into a table. We've got the data about what we rolled, so we have those roll values. We've got this table of the values and the frequencies of occurrences. Now, it might be helpful to also visualize the data a little bit so that we can start making sense of what's happening here, right? Well, There's two different ways we might do this for right now. We might use a histogram, which is really just a bar graph that plots the values against the frequencies. Or we could use a frequency polygon, which is a line graph that does the same thing. So we'll look at what those two look like using this particular set of data. We've got our rolls along our x-axis, so what the values are, right? If I rolled a 1, if I rolled a 2, etc. And we've got our frequency in the y-axis. And the same is true for the line graph below. This would be the histogram. This would be the frequency polygons. Having said that, there's a few things I should note about these two graphs. There's something wrong with both of them. First, I didn't label what they were. I didn't label my y-axis. And I didn't state what these are. So, to fix that really quick, values, frequency, so having properly made this first graph, what I should have done is stated that the x-axis is the axis of values, of roll values, that the y-axis is the axis of frequency, and stated what these represent, what this graph as a whole represents. And again, I should do it down here as well, but because I don't have enough room down below, I'm not going to. So really, thus far, all we've talked about are a few definitions and some ways of, one, organizing data, and two, visualizing it. For the most part, that's all this lecture is going to be about. Different ways of visualizing the data and making sense of some of it. Next, let's look at stem and leaf graphs. Really quickly before we move on to stem and leaf plots, I just wanted to make a point about the word data. The word data is plural. It is incorrect to say the data is. We should instead say the data are. I just wanted to make this point because it's a common mistake that shows up all over the place, and it's kind of a, for me, myself, a personal peeve, because I didn't know this for the longest time. When I did, I was like, thanks English teachers for telling me this. But no, the data are, not the data is. It is a plural. Cool, let's move on to stem plots. At the end of the day, all a stem leaf plot really is a method of organizing data in a way that produces a visual effect similar to a histogram, while simultaneously preserving the data itself. So consider in a histogram, if we were to group, for example, something like 0 to 10, 11, my mistake, 0 to 9, 10 to 19, 20 to 29, so forth and so on, and look at the frequency of how values occur in those groups, we lose a lot of data there. For example, 0 to 9 might have a frequency of 2. Was that data point a 2? Was it a 3? Was it a 4? Was it a 5? So forth and so on. We don't know because it's not there. But using a stem leaf plot, we can see it a little bit more clearly. Having said that, let's look at this example here. So we've got an exam that's out of 119 points, and these are all the points associated with that exam. So student 1, 2, 3, so forth and so on makes each of these total number of points. And we're going to put this into a stem leaf plot. And to do that, we start off by saying, let's consider what our stems and our leaves are. A leaf is the unit value on every one of these numbers. And a stem is everything other than that unit value. Start off with, let's look at this first value, 113. Well, the leaf would be 3, so the stem would be 11. So we have 11. We'll write down 3 here. Following that, we have 112. So we would write a 2 down here. 90, our stem would be the 9. We'd write a 0 down here. 93, we would write a 3. 8, 101, our stem would be the 10, and our leaf would be the 1. 104, 101, 103, 108, 107, 111, so 111, 111, 1, 70, we'd come down to the stem being 7, we're at a 0 here, 92, 95, there was one student who made a 0. All right, notice now, this sort of looks like a sideways histogram, doesn't it? So it kind of looks like a histogram, but it looks like a histogram that, like I said before, it preserves the data. I can look back at this stem leaf plot and I can say, all right, I had 1, 2, 3, 4, 5 students make in that 90 range. One of them made a 90, one of them made a 93, a 98, a 92, and a 95. This is what I mean about it preserving data. So this is really what a stem leaf plot is. Having said that, let's move on. Before we move on to section 2 of chapter 12, really quickly wanted to go over this notation here. This is the Greek letter sigma, and when we see it in math, it generally just means to add. As a couple examples of this, we might see it written with some index value and where it starts at below and where it ends at above the sigma, followed by whatever we're adding up. So for example, we're adding n together. And we're going to start n at 1, we're going to end n at 4. So we're going to say n is equal to 1 plus n is equal to 2 plus n is equal to 3 and 4. So what we're going to see is that this just means add up all the values from 1 to 4. That's it. That's all it's saying. Just add up. Where you start, where you end. And this tells you what's changing as you're adding things up. So, we might have a bunch of data with an index on it. And that index just tells you this is data point whatever my index is. If that's the case, we can say add different data points up from when our index is equal to 3 to when our index is equal to 5. And that way we would have the third data point plus the fourth data point plus the fifth data point. That's really all this index means. So this could be A3 is equal to like 400. A4 could be equal to -30. A5 could be equal to pi. And in that case, we'd say 400 plus the negative 300 plus the pi, or whatever it is, you know? Similarly, we could put an equation inside. We could be saying, all right, add n plus 1, the quantity squared, together from when n is equal to 0 up until n is equal to 2. So we would substitute in 0, 1, and 2 for n, just add all those together. That's really all this notation means. Generally, however, saying that, in this class, we're just going to see it used this way. In this form, in this context, all it's saying is add up your data. So this is the data value, add them all up. Having said that, we might also see it in one other form. And what this means is add the data value times how often it occurs. So here, we would be counting each and every time that data value shows up. And here, we're saying, take each unique data value and multiply it by the times it shows up. And you'll see more of what I mean in just a second. In section 2, all we're really talking about is measures of the centers of a data set. Now you might be hearing that thinking measures, plural, centers, plural. Yes, there are multiple different measures we're going to be using and multiple different types of centers we're going to be using. To start off with, let's talk about the mean. The mean is really just the average of your data set. Now there's two different ways we can calculate it. We can add up every item in our data set and divide it by the size of our data set. Or we can add up every unique item in the data set times how often that item occurred, and then divide all of that by the number of items in our data set. We have the median, which is just the measure of what number is in the middle of our data set. So if we were to organize our data set from largest to smallest, smallest to largest, we'd go through and say 1, 2, 3, 4, and find where that middle indexed value is and say, ha, that's our median. If there's an even number of elements in our data set, then we find the two middle values and we average the two out. If there's an odd number, we just say, all right, find that middle value. The mode is the most commonly occurring number. And the mid-range, well, that's just averaging out the largest value and the smallest value in our data set. So looking at an example, let's take a sample from our previous data set. That data set was, of course, about grades, right? We've got the values 0, 95, 92, 70, 111, 111, 107 for the number of points different students received. Well, it's easiest if we first just go ahead and organize this from smallest to largest and find the median. I think it's easiest to start there. So I went ahead and did that, organized it from smallest to largest. And I said, all right, cool. 1, 2, 3, 4. 1, 2, 3, 4. 95 is in the middle of our data set. So it must be our median. Then I said, all right, cool, let's find the average now. To find the average, we added up each of the elements and we divide by 7. Or we can go through and say, add up each of the unique elements times its frequency. So 0 was a unique element, it occurred only once. 95 was a unique element, and it occurred only once. 92 occurred once. 70 only occurred once. 111 occurred twice. 107 occurred once. Add it all up, divide by 7. Now looking at this, it's pretty easy to see which value, which data point is the most common, right? 111 is. So that would be our mode here. And to find our mid-range, took 0, added it to 111, and divided by 2. That's really the whole idea here. Mean, median, mode, mid-range. Next, section 3, we're going to be talking about measures of distribution. What we're really getting at in 12.3 is just measures of distribution. And we're looking at it through 3 different measures. We're looking at it with range, the deviation from the mean, and the standard deviation. The range is literally just how wide our data set is. You subtract the smallest value from your largest value. And that's the range. How wide is that? The deviation from the mean, it says, let's look at any one particular data point and look at how far it is from the mean. So, how far does it deviate? What is its deviation from the mean? Standard deviation, on the other hand, is a little bit more involved. And it considers all of the deviations from the mean. To calculate standard deviation, we take the square root of the sum of all of our deviations from the mean squared and divide that sum by 1 less the number of values we have. Okay, that's a lot. So let's look at what this looks like. To start off with, well, not even to start off with, let's use the example that we were just talking about previously. Went ahead and calculated out what the mean actually is, as opposed to showing it in that huge long series. That mean was approximately 83.71. And we can start by saying, let's draw a table where we can start to calculate our standard deviation by saying, let's draw out a table where one column is going to be our actual data points. Our second column is going to be the deviation from the mean. And our third column is going to be the deviation from the mean squared. So we've got our data points, 0, 7, 92, so forth and so on. And from them, we subtract our mean. From there, we square it. And now, we're going to add all of these together. After we add them all together, we're going to divide by 6. And we're dividing by 6 because we have 1, 2, 3, 4, 5, 6, 7 data points. 7 minus 1, 6. So we divide by 6. And like I said, we add all of these up. We're going to find that the standard deviation, before we take the square root, is 1,570 point blah, 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 blah numbers. Cool. Now we take the square root of it, and we find that the standard deviation proper, is 39.63. What this is really doing is saying, what is that normal deviation? How far? What's the standard deviation from the mean? That's really all it is. Having said that, If you have any questions, by all means, please feel free to shoot me an email. I know going over chapter 12.2 and 12.3, I was kind of sparse with examples. That's because the book has a bunch and I would like y'all to look at those. I think it does a better job explaining than what I here on the board can do through video. Having said that, again, like I started to say before, please shoot me an email if you have any questions. In the meantime, have a good one, guys.